Hi and welcome to a new test and teardown video. Today we will be looking at this power supply EC3-01. It is made by the automatic Copenhagen.
Thank you very much. And the cool thing about this one is there is only one meter. So they use this switch to select two different voltage ranges and three different amp ranges. There's actually only one thing that I'm a little bit worried about, and that is the current setting here, or current limits. What if this one is set for full 1 amp, and then you're messing around with some small and tiny stuff, and then you accidentally short? Are you going to break the meter, or is it somehow changing the limit, or how this meter is working? This is something I look forward to figure out. So let's just put everything here in the middle, and let's put it in the voltage mode. How about we just try and power this up and see what happens? Straight away, nothing happens here, and 1810 watts, and the watts is actually falling. Oh, look at that! It looks like it's working, and this one is also working. 30 volts. Why is this? Okay. Don't go to... Okay, that is of course the fine. Yeah, obviously. So fine is good. And then we can... Okay, there's a little bit of noise with the... Okay, that is funny. Look at that. The more output voltage I got, the less fine is working here. That is funny. Here's no at all, and then all the way down, and then fine is 0 to 8 volts. All right, that was something. And this is the 10. Yeah, that looks all right too. I think we should, definitely test this thing with a little load. So to make this a little bit more visual, I took my own load here. So I set the current for 800 milliamps, and now I change this meter to 1 amp and crank up the current limit here, and that seems to be good. So let's try and see what happens here. Look at that. It's unstable. So there is some sort of an unstable thing. But this meter is so slow it can't reveal what is actually going on. Look at that. It goes from 300 to 500 or something like that. It's completely unstable, and it's not visual here. Oh, that is funny. And look at that. I think it is actually also visible on the voltage. So when it is in current limit, it just goes all the way down to almost no voltage. And that is a thing with a constant current source, right? When you're in constant current mode with a power supply like this, then voltage just goes all the way down, and obviously this is what this can't really like, or it just don't like it, right? So what happens here with the current and the voltage? Doing, and that is of course because when it goes, yeah, exactly, from a low voltage up to the 26 volts, and then it's, yeah, that's a little bit funny. All right, enough playing around. It looks like it's working, definitely. Let's crank down the current 250, and then test. Ooh, that is nice. Let's try. Nice and good ammeter. So 80 milliamps. And it's also good. Alright, I'm quite happy about that. So, ooh, when you're poking around with the voltage, then yeah, there's definitely a little bit of something here. I think it's time to look inside. So now we are inside, and it is actually a little bit impressive. That is a nice design. Like a good stable mechanical construction here, and yeah, a good safe distance from the main switch to chassis. That is also quite alright. This is the mains input connector. Oh, let's get some light so we can see what we're doing down there. But what is this big coil doing? All sorts of resistors down here. This is built a little bit like tube gear would have been built, right? So I guess the time for this is about 1960, 1970 something. About that. We can maybe be a little bit lucky to find some date codes. See, we got a PCB here in a socket, I suppose. And the 3 power transistors here, they are actually also in some sort of a socket. I think this is a socket, right? Oops, this one is supposed to be that loose, I don't know. No, not hot at all. We got some discharge bleeder resistors here. We got some funny metal thing. Ooh, the fuse. I need to fix that. And here is the automatic. And then this. I don't know if I can show you guys this EC3, 01 040. And then there's a very big power resistor here. Selenium rectifiers. Ugh. I got some other diodes going to chassis. They look like they're in parallel. Yeah. And then I think that is actually also a selenium rectifier down here. I got a lot of transistors and stuff on that board. Yeah, but it's a quite beautiful design, I must say. We got a lot of different windings on this mains transformer, so that's probably what all those rectifiers are doing, all the different voltages and good stuff. I will try and see if I can unplug the modules here. Yeah, that one was easy to unplug. There was a locking metal thingy up here, and then it pulls out. And it looks like we got a driver here. That one is a driver, and then the 2 others, there are output. Oops, what is that? 2N457A. That is what it's gotta be. And then the other board here, I nearly broke everything in my attempt to pull this out. And then I realized, ooh, there was this locking mechanism. What the heck is that thing? We got a lot of transistors in there. What is... No? What is it? I mean, I normally know what stuff is. But this one... I actually don't know. We got a lot of thingies in here. Now I am very curious to figure out what that is. We got maybe a little bit of... What is written here? Is that 1966? Yes, it is. That is definitely 1966. What kind of lock is that? We got initials, AP, and then 1966, and then some other initials. Ha ha ha. So that is how old this thing is. And here's an MF and 64. Okay, so maybe this PCB is designed in 64, and then this was manufactured in 1966. Yeah, that looks... I mean, it actually looks quite a lot like that, right? With the selenium stuff, and we got more of that. I don't understand that big coil down there. Maybe it's a filter. Oh yeah, maybe. Why would you have those two? And then, yeah, that's probably just an inductor between the two capacitors. Jensen. Sometimes you can get lucky to find date codes on those as well. But that is not the case. Yeah, I need to go and give this some compressed air. This is dirty. So I took away the bottom, just so we can see how beautiful this is really made. I am actually a little bit impressed. You gotta say that this is nice, right? And this is the thing that I thought would have been an inductor, but no. You know what this is? This is a resistor with a very high accuracy and a very low temperature coefficient. I can't really read all about its specifications here, but I guess I see a 5, so that's probably 0.5%, and the ohm is, I don't know. I'll try and see if I can figure out what it is. But that's probably a current sensing. Oh, type MM5. Oh, well, we just can't Google that, can we? Made in Denmark, precision resistor thingy. And also the other resistors here, they're also 0.5%. And when I see stuff like that, and also the way that it's sensing all the way down here correctly, all this is just super good. Yeah, this is actually quite impressive. Very good design. And so the rear plate here, you can actually just take out those 4 screws, and then this entire plate will come out, and then it's easy to update the connector to a more modern IEC type. So that means this power supply could get back to service again. If you like old cool vintage stuff, well, why not? I mean, it is actually working. I'll try to measure some hum and some ripple and regulation and stuff like that. And let's see how well it performs. I just can't forget this funny component. So what I did is I traced those 2 connections down here in this connector. And look at that. The connector is numbered. I don't know if it's easy to see. Yeah, here we go. And then the mating connector down here is also numbered. So it's the white and the yellow one in the middle of the picture, and those go to the output. Really? So, and of course I powered this up and double checked. Yeah, this is the output. So what the heck is this? Look at that. I just poked it out of the board. I needed to see what the heck that is. But that is actually 11 diodes in series. So they made this really cool module here. But for what reason? Why is it we need to have all those diodes in a big chunk of aluminium? And it also looks a little bit like the design here. You could just solder them in here and then, yeah, and they measure just like a diode. So what the, weird. Now it's out because it's directly on across the output, right, on the board. So that means, of course, I can take it out and just power it up and try and play around with it. And of course, everything works completely normal, the way that it was. So I guess that is a like an overvoltage protection circuit. It's probably just Zener diodes. Don't you think so? Why are they doing it like that? Okay, I managed to figure this out. 7 of them, they're Zener diodes, 4.7 volts. And the last 4 of them up here, that's normal diodes, 0.8 volts. So if I add all this together, it's 32.6 volts. I just tested this at 100 milliamps. So the reason why they're using 7 4.2 volt Zeners, that's of course not to overheat each of them when they protect against a failure in the power supply. When something breaks here, you're going to get a very high output voltage if the regulation or some stuff breaks, right? And you don't want to blow up some external stuff. It's much better to have this sitting here, and then it's going to hold down the voltage to 30 volts or 32 volts or whatever. It's going to take the fuse, and then it's quite safe, I suppose. But that is a funny device. Well, I've never ever seen anything like that before. Why don't you make a power Zener with a transistor and a Zener? I mean, this is just a very expensive way to do this, right? It's a very simple construction to make an active Zener diode with just a transistor and a Zener and a resistor. That's all you need, right? And just put it on one of those, and then you'll handle all the power. This is not going to handle anything, right? It's 30 watts. Couldn't help it. I just wanted to find out about this really cool power resistor here, and it is 1.501 ohms. Ha! How nice is that? Cleaned up the contacts to the resistor and redid the measurement, and I'm just saying that this resistor would have been very expensive back in 1966. So I've been measuring a little bit more around in this unit, and as you can see here, there is a lot of ripple. So 0.5 volts peak to peak ripple at 0.5 amps. So there's definitely some capacitors that needs replacement, and I've been through everything with a thermal camera, and I don't see anything that is criminal, crazy, or way too hot or anything like that. It's all doing exactly as it's supposed to do. Here's this really big power resistor, and that one is running a little bit warm, as you can see here, but of course that is not a problem at all for this type of resistor. I just don't know where it is in the circuit. Why is this supposed to be running that warm? All the bleeder resistors, and they're perfectly fine and all that. And I also went through that control PCB, and I don't see anything alarming here at all. But it could be fun to see if I could easily find that broken capacitor. My search for faulty capacitors, I've been through all the capacitors, and yeah, okay, I do find some capacitors that's not really good, and I do replace them with new capacitors, and it is improving, but it is not solving my problem. And then I start realize, hey, there's also a capacitor here at the bottom. I actually didn't look at it so deeply, and why the heck didn't I do that? Because look at that capacitor. I mean, there's nothing left. This terminal is completely corroded, and it's not. So we got two other wires, the two blue ones, blue and white ones, they go to the negative, and that one. So yeah, I just need to take that out. That is definitely, it has to be that one that is causing the problem. I am so happy. See that big bad boy here that didn't work at all? I just put this tiny little 100 microfarad 100 volts because this one is actually 200 and it needs to be more than 63 because I measured 75 volts at that point before I put on a capacitor. So you need a 100 volt capacitor here. I don't really like, why are you using those high voltages when it's only a 30 volt output power supply? So that's a little bit crazy, but that is just the way it is designed. But with this capacitor, look at that, we have a flat line. And let's crank on the output. See, we are now loading the output, only half an amp. Okay, good. Tick, 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 tick. Yes, 10 millivolts. That is nice. And I think if I just, this noise and everything here, this is going to be the same if I turn this off. Yes, exactly. This is no load. And let me turn off the mains. And then you'll see that the noise and stuff when it's finally returning. Yes, you see, it is exactly the same. And it's because this whole construction here is going to pick up a lot of noise and stuff. And it's going to go in here because I got switch mode power supplies and such. And this is the background noise for that. So this is totally silent now. And I will call it a day and close this up. Oh, happy me. And see you again tomorrow. Bye.